Hello lovely people. Today we're going to have a video about amplified distortion measurements, and I'm going to tell you how to read these graphs. So this is a video that I'm probably supposed to do like right before I started measuring amplifiers, but I'm doing it a bit late, so apologies for that, because I was expecting, it's not expectation, but it's just I thought that everybody knows how to read these measurements, but I do get a lot of comments that people asking what does it mean, how to read it, and what it actually is. So today we're going to cover quite a few measurements. What I do, it's not standardized, these measurements, it's just what I do when I'm measuring amplifiers and DSPs. And I'm going to tell you about every single graph, and I'm going to show you some examples of like good measurement, bad measurement, it's kind of in the middle measurement. So I do mainly 5 or 6 different measurements, maybe 7 measurements, depending on what I'm testing. And the main graph that I'm starting is this one. So this is a measurement of THD plus noise, so total, this one, total harmonic distortion plus noise against the level. So the level is the actual power level that the amplifier is outputting. Now, I didn't put any names here, I didn't put anything because these values for us don't really matter for this specific video. What matters is the actual trend and what we can see here. So on the left side on this column, you see the percentage. So 100% would be 100% distortion. And then you're going to go lower, 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 and lower all the way up to like 0.1, 0.1, 0.01, and all the way down 0.001. Now, the question is, the main question probably is, what is good distortion and what is bad distortion? Meaning, how low this graph supposed to go. If we have a look at this trend, so this graph that it goes like from up, it goes down, there's a low point, and then it shoots up. This is a very typical graph for kind of all the amplifiers. Some might have a bit different, but in general is kind of the same. So what's happening here at the bottom, you see power in watts. So again, the actual numbers don't matter, but what you need to know is just basically how this amplifier performs stage D-wise if you're increasing the volume. So here we have somewhere in the middle like 1 watt, then we have 10 watts, 20, and here we have 100. Now, this graph shows that, and this is the case for most amplifiers as well. At the bottom here, we have like what is compromised, what this graph is compromised of. So I have a fundamental, which is the actual sine tone that is at the top. It's always going to be 100% because we're playing a sine tone. And then we have some stuff. So we have, I reduced the harmonics because REW shows all the way up to 9th harmonic. And when I was looking at them, it's kind of too much graphs, too many stuff. So what I did, I left only the 2nd harmonic and the 3rd harmonic. So you can see how it compromises the 2nd harmonic here, this 3rd harmonic. Then we have the THD, which is the actual THD of the amplifier. We have floor noise, which is somewhere like all the way down there. And then we have THD plus noise because this green one is noise. So let's actually untick everything and let's have a look at the noise. This is the noise performance of the amplifier. When you have very, very low volume, the amplifier is basically dominated by noise, the internal noise that is caused by the circuit, by the components, and by everything else. So this is basically noise. Then you have THD, which in this specific amplifier, THD is much lower than the noise at lower volumes, and THD increases the more volume you give. And then basically when you clip the amplifier, then you have THD shooting. Exactly the same with some harmonics, like the 2nd one, it goes there and this. So we can see that this graph, THD versus level, in most cases is going to be dominated by noise at the lower power levels and dominated by THD at higher power levels. Now, we will see different percentages of this. In some amplifiers, it could be slightly different, but this is kind of very, very typical. And this is kind of a crossing point where THD overtakes the noise. In THD plus noise is the actual sum of all the components of everything. Now, if we have a look at the percentage, everybody says like the rated power and everything, the amplifiers usually are rated at 1% THD plus noise, so at this point. And this specific amplifier, if we just cross this like here, we can see that this amplifier is doing 100 watts at 1% THD. Now, you wouldn't want to play an amplifier at 1%, like at the maximum volume. That's why headroom is good, because you can see this rise of THD is very, very sharp. And if you increase it by another like 20, 30 watts, it's going to go up to 5, 10% and even higher. So it's not the best idea to play the amplifier at this much level. The best amplifier use case is in this area. For this specific amplifier would be something between like 5 watts and all the way up to 70. So this is the area where the amplifier is the cleanest and it performs the best. Now, if we have a look at the THD at this side, at this specific level, like the lowest it can get is 0.005%, which is an amazing value. Now, what is amazing, what is good, and what is bad? And again, this is very relative, and this is my opinion only. So feel free to disregard it. Feel free to comment however you want. But to me, a good amplifier is something that has a THD below 0.1%. It's good. It's kind of okay. It's not really a problem. If you have an amplifier that is THD is 0.01, it's an excellent amplifier, amazing amplifier. This goes even lower. If you have something lower, like something 0.002 or 1, this to me personally is like top of the range, top of the class amplifier. So far I measured only one that measures so low, and that is a Alpine PDX. Now all these graphs, you can find them in Distortion Factory, which is a Facebook group designed for, like, I designed it just to show these graphs. So as I mentioned, 0.1 is kind of okay, it's not bad, and 0.01 is an excellent. So you can see that this amplifier, I'm not gonna tell the name, but this amplifier performs extremely, extremely good. Now let's have a look at worst performance. So this is a very, very good performance. If I switch to this graph, for example, you can see there's a totally different picture. If I flip between this and this, you can see that it looks very, very different. You don't have that deep, deep knee where you have, but you have kind of a flat THD. And this is, if we take something here, it's like 0.03. So again, it's below 0.1. It's not that bad at all, but you can see that this performs much, much better than this. However, on this one, we can see that it has a bit more power, 1% THD, it's like 130 watts, but again, those watts doesn't matter. And here you can see there's a different composition of the THD. The second harmonic, you can see that it goes like this. So we will be talking about harmonics a bit later when I'm going to show you the 1 kilohertz sine tone. And oh, I didn't mention probably, so this THD versus level, I measured with 1 kilohertz sine tone. It's like a, I want to say industry standard or something. But yeah, so this amplifier performs a bit worse, but it's still very, very good performance. Now let's have a look at the bad one. This would be, in my opinion, a bad performing amplifier. You can see that the lowest it gets is 0.3 only. And then like here, if we have a look at this, 18 watts, 0.5% of THD and 1% you have here. So in my book, this is quite poor performing amplifier, and you see like this in other amplifiers, all this range in the lower power is just noise. But for this one, you can see already you have like second harmonic, and no, it's not clicked. Third harmonic is there, and it's like THD as well, dominated, and the noise is lower. So this for me is a bad performing amplifier. Not only because of the THD level, but as well because of the components that compromises that THD. So this is just an example. Bad, good, very good. Now, the second measurement that I do is THD versus frequency. So I do a sweep from 20 Hertz all the way up to 20 kilohertz. And this sweep is measuring THD at specific points at frequency. So you can specify how many points. I think I have 3 points per octave. So like between 20 and 40, you have 3 points, and so on and so on. And this shows like linearity, I want to say, of THD. How linear is the THD? Depending on the frequencies. So this specific amplifier, you can see the THD in general is very low, is below 0.01. So this is an excellent measurement. However, we see that at the higher frequencies, we have something like popping up here, which is, yeah, like the second harmonic, and the THD as well, it just pops up. And we have some stuff rising here at the lower frequencies. But again, this is below the noise, because the green is the noise. So again, this is very, very good measurement. We see all the harmonics way below the noise, apart from here, but it's still very, very good. Now let's have a look at the worst performing amplifier, which is this one. So for this one, we see that the THD level in general is a bit higher, because we can see here from this point up to here, it's not big increase, but it's still increase. So more THD. However, if we have a look at the components, again, we have a similar picture where we have the second harmonic is higher, much higher than the previous measurement, and it's kind of almost following the noise. So the noise you can see here, again, it is dominant noise, but the harmonics are so high, so close to the noise, that the THD plus noise is actually higher than the actual noise. However, in this one, you can see that the noise in THD plus noise is the same, because harmonics are all the way down there. So this, in my book, is a worse performing amplifier because of the, again, composition of the THD. Now, a bad amplifier would look something like this. And this is a total mess. So we have noise, which is, from all of these, the noise is the lowest. And THD is dominated by, THD plus noise is dominated by the actual THD of the amplifier and all the harmonics. And like here, this issue was happening here. I have absolutely no idea. Then we have rising THD towards the lower frequencies, and we have rising THD towards the higher frequencies. So this amplifier, to me, even if it's kind of low, you can see that even this peak is below 0.016, so it's below 0.2. And like the whole thing, if we kind of grab it here, 0.003, which is kind of okay, but the actual composition is just a mess. Now, are you gonna hear it? Probably no, but this is the thing, like, in these measurements, I'm not talking about what you actually hear, but how amplifiers compare to each other. So if you compare this and this, you can clearly see which one performs better and in general is a better design. So that's the other one, THD versus frequency. Now, the other thing that I do, I test the linearity. So if we go to SPL now, I'm going to untick this one and this one. So this is, I will need to flip it to SPL. And this is SPL, which is like loudness, and 1 dB increments. So 1 dB increments, and we can see this if I click here. It's very, very extremely linear. So we have difference between like 20 hertz and 20 kilohertz, and the main like line, there's only less than half a dB difference, which is, in my book, it's very good linearity, because obviously you're going to have some roll off at the top end and the bottom end, because bottom end is the subsonic filter and the top end is because it's supposed to be there, because you don't want to have switching noise, especially on Class D amplifier, switching noise coming in. So it has to chop off the top and bottom. But this linearity is very good. Now, what would be a bad example of linearity? Something like this. Now, again, if I remove this and we have a look at the scale only, this goes from 56.6 to, let's say, 55. So it's like 1.5 dB. Plus minus. If we have a look from this point, kinda, it's like 1 dB difference at the bottom end. Now, again, it's not a big of an issue, but it just shows that either the intent of the amplifier was to have a tiny bit more low end, which is like just 1 dB, but it's probably still, you can hear it at 40-50 hertz, 1 dB difference. Maybe, I don't know, I'm not going to go into those details, but this comparison just shows a very good, well-engineered frequency response of an amplifier versus something that is not as good, or it was done to manipulate it on purpose. But again, I'm not sure how it is, but this is just an example of, in my opinion, good frequency response and not good or bad frequency response. Now, let's go to dBr back and let's have a look at this. So this is a spectrogram, like a spectre of 1 kilohertz tone. Every time you play a single tone with an amplifier, DSP, or whatever, what is producing music, you will have some harmonics. You will have it, unless you have something extremely good DAC, maybe like a DSP that measures extremely good, then you're not going to have any harmonics. So what is a harmonic? Harmonic is a tone that is repeating like 2x or 3x of the fundamental notes. So if I'm playing 1 kilohertz tone, which is like here, you can see these spikes, which one is at 2 kilohertz, then 3 kilohertz, then at 4 kilohertz you cannot see anything, and then at 5 kilohertz, and so on and so on. So the more harmonics you have, the worse the THD plus noise is, because THD is total harmonic distortion. So you saw like in this, for example, in this one, where you have these second, third harmonic and stuff. So this is 1 kilohertz tone, the fundamental. The second harmonic is 2 kilohertz, which you can see here, and this is 3 kilohertz. And we can add like 4, 5, 6, and all the way up to 9. And here you can see the actual composition instead of like the graph. This is, usually I do this on 5 watts of power on a fixed power level, just to make sure that all amplifiers are measuring at the same power level. So this is done at 5 watts of power. And you see, this is a dBr scale, which means that fundamental note is always going to be at 0 dB, which is here. And then you can compare the other ones. So the second harmonic, this one is at minus 95 dB, which is extremely low. Then you have the third harmonic at minus 100, and the fifth one minus 114. This wiggly thingy at the very bottom is the floor noise of the amplifier. And again, it could be higher, it could be lower. So in my book, something like this is a very good measurement. Now let's have a look at something worse. And yeah, so this shows total harmonic distortion plus noise is minus 82.3. So what it does, it basically, REW, it calculates all the harmonics and all the noise adds everything together and gives you a number. So there's a very good number to compare between different amplifiers. Now let's have a look at the other one, which is TG plus noise minus 75. So again, the bigger the number, because it's negative, the bigger the number, the better. Now, the difference is 10 dB. Now let's have a look. The difference is this. So this is a different amplifier, and you can see if we compare it, the floor noise is higher, which is this. And then we can see, if I remove this, we have more harmonics. Because on this one, we had only second, third, and a little bit of fifth. But for this one, we can see second, third, fourth, fifth is not there, sixth, seven not there, eight, 10th, and so on and so on. So this one, this amplifier has more total harmonic distortion, and that's why this number is lower, which like lower, higher, depending how you look at it, is a negative. So since negative is a lower number. And yeah, so this would be a worse performing amplifier. Now let's have a look at even worse performing ones. So this is again 10, almost 10 dB, 82, 75, this is 65. And this is a 65 dB. And again, we can see the floor noise again is higher. And here we can see a total mess with harmonics. Second, third, fourth, fifth, sixth, and all of them. And you can see here, basically, I have all the harmonics, and they're much, much higher. So if you compare this versus this, you can see that there's a huge difference between how these two are showing. Yeah. So again, good, worse, and the worst. So this is 1 kilohertz tone. Now, another thing that I do is I play a multi-tone, which is very similar to 1 kilohertz. It's just instead of playing one single tone, you're playing multiple tones. I'm not sure exactly how many. I think it's like 30 or 31 tones. And you have something like this. So you have like tones, and then you can see the floor noise, and you can see how it deals with the lower frequencies, good or bad. So this, in my book, again, it's kind of a good measurement. So, just to mention these numbers, again, we have 82, 75, 65. So even 65 is not as bad, but you can see that there's loads of harmonics. So in my book, like, I want to say below 70, about 80 is a very good amplifier if it does 80. Below 70 is still good. Above 60, it would be very bad. Okay, let's do this multi-tone. So again, multi-tone, all tones display like this. You can see some noise here because this is the floor noise. You can see the floor noise is rising at the top end, and you have the whole response noise here rising at the bottom end as well. But still, this to me is a good response. Now, I don't have a specific number that I'm aiming for when I'm looking at this. I'm just looking at the general like view, how it looks like. To me, it looks kind of clean, just a bit noise here and here. Now, if we have a look at something like this, I'm going to remove this one. You can see that the floor noise is higher between these two, but the biggest difference is the low end. So you see with this one, you have much noise at the lower end. Now, you're not going to probably hear it because for low frequencies, we don't perceive like noise and THD and everything as much, so it's not a big of an issue. But if you just compare these two measurements, you can clearly see which one is better and which amplifier is better designed. And now let's have a look at the worst occasion, which is something like this. Now this, in my book again, it's a really bad measurement. Even just because if you have a look at the fundamental. So the fundamental on this good measuring amplifier is always at 0 right there, but for this one, even the fundamental is not at 0. So that means that like the frequency response is extremely non-linear. And here you can see loads and loads of noise, and the floor noise is much higher. So between like these three measurements, you can see good, okay, and this is bad. So yeah, so these are the measurements that I usually do when measuring amplifiers. And these measurements, what I do them in a resistive load of 4 ohms, then I do at 2 ohms, and then I do like bridge channels and so on and so on, because the performance of an amplifier, depending on the load or if you bridge or not bridge channels, is gonna vary and it's gonna depend. And again, it's very interesting to see how it depends on those stuff. So yeah, there usually is a lot of measurements, but just for you to see. And I hope this video kind of explained to you what to look for, what is kind of good, what is kind of bad, and hopefully you're gonna be able to read these measurements much easier next time you're gonna see something like this. Unfortunately, nobody's publishing these measurements because I don't know why. Maybe they don't want to see that their product is not as good, or it's just too much work. So if you want to see any of these graphs, head down to Distortion Factory. I'm going to leave the link in the video description. You can check it out. And thank you very much for watching, guys, and I will see you in the next one.